Okay, let's work through a few of the exercises from exercise set 3B. In each case, you have two propositions labeled, one labeled A, one the other labeled B. You're asked, does A imply B? Does B imply A? And are they equivalent? Now, for this homework, I'm going to want you to show your work. I need to see some truth table work to see how you arrived at your answer. I'm not requiring complete truth tables in the exact same way, so use your discretion, but I need to see some work, and the more work you show, the more partial credit I can give you. Okay, let's just start with the first one. Okay, now if you still think that these are equivalent, I'm going to prove to you once and for all that they are not. This says P and Q are both false. This says they're not both true. One is false. We're going to see how that works for implication. This implies this, but we'll see how things shake out for these exercises. Okay, so this is A, this is B. I know we use a lot of stand-in letters, but right, this is our we're calling this proposition A, proposition B. We're going to see, does A imply B? Does B imply A? Are they equivalent? A arrow B a tautology? Is B arrow A a tautology? Are they equivalent? Okay. We go true, true, false, false for P, true, false, for Q, and we do the truth tables. First, again, I think the method Hardegree is suggesting works best. Do the truth table for each individually. Right? Here's the main connector for A. Here's the main connector for B. So we go true, false, false, false for under the and, but then the whole proposition goes false, true, true, true. Oh, look, three trues and a false, just like an or statement. They're not both false. They're not both true. They're not both true. One of them is false, and that's true in 3 of our 4 scenarios. Just like one of them is true in 3 out of our 4 scenarios. Look at that. Okay, at least one, right? Okay. Not P and not Q means they're both false, which is only true in row 4 here, right? So we go not P. False and false is false. They're both true in row 1, so the statement that they're both false, definitely false. Okay? P is true in row 2, so the statement that P and Q are both false. False, false. They are both, P and Q are both false in row 4. Okay? So we get true, false, 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 false. Sorry, we get false, true, true, true for this one, and false, 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 true for this one. They're not even that similar, right? They're not even that similar, although they, in ways, they might look similar. Okay? So here we go. Does A imply B? Remember what that means. If you know that A is true, do you know that B is true? If you know that they're not both true, do you know that they're both false? That P and Q are not both true, do you know that they're both false? Okay? And look how that shakes out. False, true, true, true. False, 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 true. How did I get these? I plugged in the truth value into the main connector for A here, false, true, 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 and I plugged in the truth value under the main connector for B here, under B. And then I do this arrow statement and see if I get a tautology. Why do you need a tautology? Because we're talking about logical implication. Do you know for sure that when this is true, this is also true? You do not. There are times when this is true, but this is false. Just because I told you the Mets and Dodgers did not both win, you don't know that they both lost. So if you had money on they both lost, you have to check the paper. False arrow false is true, but true arrow false is false. Here's a scenario where this is true, but this is false. Same with scenario 3.
Yes, they both have the same truth value in scenario 4. A implies B in scenario 4 because they're both true. But A does not imply B. You need this to be a tautology for A to imply B, and it's not. That's why this is the main reason we introduced the concept of tautology. Now, we've done this for single propositions, but this idea works for arguments. We can now define a valid argument as an argument where the premises together logically imply the conclusion, meaning when the premises are all true, the conclusion also has to be true, right? Which goes back to chapter 1. But now we have a technical definition for it. I'm skipping 3C would have you do a truth table test for multi-premise arguments. I'm skipping that. I'm going to fold that into what we're doing. You're not going to work on those exercises, but I'll talk about the concept of validity arising out of this. Okay? All right, so not P and Q, therefore this is not a valid argument because this does not imply that. Right? I told you they didn't both win. If you deduce that they both lost, that was bad reasoning. Whether or not they did both lose, that was bad reasoning because it's possible for this to be true and this false. Right? And now we've defined, we've got a technical definition of it's possible for this to be true and this false with truth conditions. There are precise conditions under which A is true but B is false. So A does not logically imply B. Okay, how about B arrow A? Does B logically imply A? Well, B goes false, 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 true, and A goes false, true, true, true. B is only true in this scenario. So is A true every time that B is true? Yeah. False, 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 true. All right, again, this is why it was so important to define the arrow the way we did, right? False arrow whatever needs to be true for material implication to help us define logical implication. The material implication statement between them is a tautology, is how we define logical implication. And now think about this, right? It's, so to speak, harder to make this statement true. Because right, Mets and Dodgers, they both have to lose, right? There's 3 other scenarios where they don't both lose. One of them wins, the other wins, they both win, right? And so when this is true, wow, they both... Right? It brings along with it other truths, like one of them lost. At least one of them lost. Both of them lost, so at least one of them lost. Right? So yes, B implies A. B logically implies A. And again, that's what we're doing in other even multi-premise deductive arguments. We're saying if you get things right so that you meet the truth conditions for all these premises, it follows that this other proposition is also true. Right? If one of these is true, but A is false, the only way to meet the conditions of these premises is for B to be true, right? And I'll talk a little bit about how that goes, right? So again, valid argument, the premises together, which if we're being technical, the conjunction of the premises, when premise 1 and premise 2, etc., are all true, then the conclusion has to be true. But we're dealing with this with one premise. Okay, so does A imply B? No. Does B imply A? Yes. Are they equivalent? No. They're only equivalent when you get yes answers to both. Are they equivalent when you get no answers to both? No. No doesn't equal yes. They each have to imply the other, which means A is also equivalent to B. That is logically equivalent, meaning the arrow statement is a tautology. But in this case, that's not going to work. A goes false, true, true, true. B goes false, 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 true. So sometimes they have the same truth value, but these are not statements with the exact same truth conditions. Under some conditions, they have different truth values. Okay? All right? This step is unnecessary if you do these two. If each implies the other, then they're equivalent, right? Right? If the arrow goes both directions, right, this double arrow is going to also be a tautology. These are tautologies. It means they have identical truth values in every scenario. Okay. That's number 1. Let's look at number 2 by contrast. Most of these are just going to have P and Q. There's a few with P and Q and R. If you get to them and do 8 rows, that's great. You could take a look. I'll have the homework posted later. You can take a look at. I'll have to see if I include one of those. All right. Number 2 is let's see. All it does is it changes this to not P or not Q. Okay. How about these 2 statements? How do these go? Well, P and Q is true, false, false, false. So the main connector, again, is false, true, true, true. We already did that. Now we change this to or. True goes, we get false, false, true, true, false, true, false, true. Okay, here's our main connector. False or false is false. False or true is true. True or false is true. Oh, look at that. False, true, true, true. False, true, true, true. Okay? Now, when you see that the main connectors are identical, you could immediately conclude that, oh, these are logically equivalent, which means each implies the other. So that's what I'm saying. Like, I'll give you some leeway in how you use these truth tables and reason with them, but I need to see enough in the truth table to see how you got from the truth table to your answer. Okay. But let's run through it step by step here. Does A imply B? Okay, in row 1, truth value of A is F. Row 2, it's true. Row 3, it's true. Row 4, it's true. Just to show you how I'm plugging those in. Row 1, truth value of B is F. Row 2, it's true. Row 3, it's true. Row 4, it's true. Okay? False arrow false is true. True arrow true is true. True arrow true is right. All right. A implies B. Whenever A is true, B is true. How about B implies A? Well, you can see because they have the same truth value. It's the same deal. False true true true. False true true true. And so the answer is going to be yes again. True 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 true. Right. Tautology here. Tautology here. So, yes, A implies B. Yes, B implies A. Are they equivalent? You know already, since you have yes answers to both of these, but let's just show it. A double arrow B, is that a tautology? Again, false, true, 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 false, true, true, true. And we've got, they always have the same truth value. So these are equivalent. They look different, and here or here. I tried to convince you in chapter 4. Here's the proof. Here's the proof that these are logically equivalent, which means each implies the other. Each implies the other, so they're logically equivalent. When each implies the other, they're always going to have the same truth value, which means this double arrow statement will be a tautology. Double arrow statement between them. Okay, let's work on one more. I'll work on one. We haven't done anything with arrows, so I'll work on one with arrows, and we'll call this video. And that'll be your practice for the exercises, which will also be what will be covered in the homework. Okay. Let's do 13. P implies Q. Not P implies not Q. Okay, no. Remember, you got to flip and negate, okay? Just because this is true doesn't mean that not P implies not Q. Just because Ann implies Bob doesn't mean if Ann is not here, then Bob is not here. Okay, so this doesn't imply this. Let's see if it goes the other way. P arrow Q, we got true, false, true, true. Not P, we go false, false, true, true. True, false, sorry, false, true, false, true, false arrow false is true, false arrow true is true, true arrow false is false, true arrow true is true. Okay, so this one is false in the third row, right? When you said not P implies not Q, But in row 3, P is false, but Q is true. Right? So these are false in different rows, so not equivalent. Let's see what happens with implication. Does A imply B? Our truth values for A, plug those in, true, false, true, true. Our truth values for B, this is our main connector, true, true, false, true. Okay, and the answer is no, because we have true arrow true is true, false arrow true is true, true arrow false is false, true arrow true is true. Right? This is not a tautology. So there's a scenario where A is true, but B is false, and you can see now with these different truth tables, that's going to be. Does B imply A? No. These statements. Look, this is one of our instances of it's sort of deceptive here, right? And in fact, common misleading reasoning. Ann implies Bob. Ann's not here, therefore Bob's not here. No, you don't want to do that. You don't want to do that. And just to highlight that, B also does not imply A. So we get true, true, false, true for B. And we have true, false, true, true for A. True, true, true. But there's a scenario where B is true, but A is false, so B does not imply A. So no. Are they equivalent? No. And we can just double check that. Are they equivalent? No. True, false, true, true is not equivalent to true, true, false, true. Okay. This is true. Okay. Sometimes they have the same truth value, but they don't have the same truth value in every scenario. They don't have the same truth value in every scenario. So again, the answer is no. They are not logically equivalent. They are not logically equivalent. It's possible for them to have opposed truth values for given truth values for A and B. For given truth values for A and B. All right, so that's P arrow Q, therefore not P implies not Q, and that's going to be at the heart of one of our fallacies. P arrow Q, not P, therefore not Q is a fallacy. It's called the fallacy of affirming the. It's called the fallacy of denying the antecedent, because your second premise denies the antecedent. It's called the fallacy of denying the antecedent. Now I will do one more. We're going to do the next one, number 14. Just to see a contrast. Similar contrast with A and B, although in this case neither implied the other. With number 1, right? With number 1, B implied A. Here, neither implies the other. And they're not equivalent. I probably didn't need to erase all that because 14 is similar to 13. P arrow Q is our A. P arrow Q is our A. And not Q arrow not P is our B. Right? Remember I gave you the rule of flipping and negating? Flipping and negating. Okay? P implies Q. Does that mean if Q is false, then P is false? Let's see. True, false, true, true. Main connector. Of course, this is main connector. False arrow false is true. True arrow false is false. False arrow true is true. True arrow true is true. So we have true, false, false. Sorry, true, false, true, false. True, false, true, true. And same over here. Okay. So does A imply B? Yes. True arrow true is true. False arrow false is true. True arrow true is true. Okay. And look, they have identical truth values. So if you don't go through this whole thing, you just recognize they have identical truth values, that's okay. But again, I need to see your work and why you're reasoning the way you are. Enough of your work to know how you're reasoning. here under B, and these in over here under A. Okay, and indeed, A and B always have the same truth value. We get yes answers to both of these because A and B have the same truth value all the time. If they didn't, we'd get a no here. Trust me. You can think it through yourself, but trust me. Yes, yes, it's going to be yes, and we know, but we can run that out real quick. True, false, true, true here. True, false, true, true here. Same truth values in every row. Each implies the other, so they're equivalent, and indeed they are. To say that P implies Q, if Ann is here, then Bob is here, right, is equivalent to saying if Bob is not here, then Ann is not here. This emphasizes the necessary condition, right? Bob is here, it has to be if Ann is here. So if Bob's not, Ann's not, etc. Okay, so there's an example. You see how you can get a yes and a no split, and which means they're not equivalent, but one implies the other, but not vice versa. And when they each implies the other, they're equivalent. And I also gave you an example where neither implies the other, which also means they're not equivalent. Okay, so that's your procedure. That's your concept of logical implication, logical equivalence. Our definition of a valid argument is one where the premises, the conjunction of the premises all together logically imply a conclusion. How do we use logical equivalence? Well, when we're recognizing argument patterns, sometimes we can see the pattern by substituting equivalent expressions. Right? You might have an if-then statement with an antecedent written one way, and then another premise with that same antecedent written another way, and then you go, oh wait, those are equivalent, and we have rules for showing, So logical equivalent, we're not going to quite do a lot with that, but it's still an important concept here. It's an important concept in its own right? Again, I mean, law is not the only application of this, but if you're a lawyer and you're kind of keeping track of different ways conditions are stated, you got to realize what's equivalent and what's not, right? Right, you got to realize you can reason from Q being false, etc. Okay, so that's some practice on these logical implication, logical equivalence exercises from Hardegree exercise set 3B.